So we've been working with the normal distribution for the past couple of weeks now, and we should be fairly familiar with it by now. It's just a standard distribution with a mean at 0 and with a standard deviation of 1. And we know everything we want to know about the normal distribution because we have an expression for its probability density function, and we can use that to derive its cumulative distribution function. We know everything. And so the question I want to pose today is, what would happen if we took this normal distribution, I'm going to call it Z, it's going to be a standard normal. What would happen if I took this distribution and squared it? I took every value in this distribution and took its square. And well, what we can see what happened here is that I wouldn't have any negative values for one. Because we take a square of a value, if it's positive, it becomes positive. And if it's negative, it becomes negative. And so if we try and draw this new distribution, we might start it at 0. Okay. And then, well, squaring numbers, if they're bigger than 1, makes them larger. So it's going to stretch these bits in this direction. And squaring numbers, if they're smaller than 1, makes them small. So it's going to push a bit of density this way. And it turns out that what we get when we square a single standard normal distribution is sort of looks like this. And so what we have here is a density function that's starting at 1 and sort of sloping quite steeply and then evening off in its slope. As we can see here, this sort of fulfills what we were saying was happening earlier. Everything above 1 is sort of being pushed that way to the right. Everything below 1 was being pushed to the left, which gives us this density in the center. And in addition, we've got all our negative values becoming positive values. And so when we have a distribution which is the square of a standard normal distribution like this, okay, in particular of a single standard normal distribution, we call this chi-squared with 1 degree of freedom. And let's focus on the first bit. So chi is a Greek letter, and it's chi-squared, which sort of indicates the fact that we derived it by taking the square of a normal distribution. But what is it having 1 degree of freedom here mean? Okay. Well, we can write out a formula for chi-square with 1 degree of freedom. We know it's going to be equal to just a standard normal squared. We've given that standard normal a name, Z1. And so if we want a chi-square with 2 degrees of freedom, we're going to have to take a standard normal, take its square, and add it to another standard normal, which is obviously identically distributed, but independent of that first normal. So if I told you that the first normal drew a 1, that wouldn't tell you anything more about what the second normal was going to draw. Okay. And if we wanted a chi-square with 3 degrees of freedom, we simply need to take the sum of 3 squared independent normal distributions. And in general, if we want a chi-square with k degrees of freedom, we just have to take the sum of k squares of independently distributed standard normal distributions, which we can write with this summation notation here, zi squared. Okay, and so the question is, what do these distributions look like? Well, even adding a second distribution is going to create sort of an early peak. It's like this. Whoops. And so here is for chi-squared I. And essentially, the larger the degrees of freedom, the further along this peak moves. So we might have quite a large quantity of degrees of freedom. We're going to have this sort of distribution here. The important takeaway is that because we know everything about the standard normal distribution, well, we can compute all of these distributions here. And just like we can look up the standard normal distribution in a set of tables, we can look up a chi-square distribution with a certain degree of freedom in a set of standard tables just as well. So the real question is, what good is this distribution for? And to sort of get our heads around what we're going to use the chi-square distribution for, we're going to start off with a relatively simple example where I have some data. We'll call it represented by a random variable xi, which is distributed with the standard normal distribution. This is a really basic example to just get this concept across. And we already know if we've got data distributed like this, well then the sample mean for a sample of size little n is going to be normally distributed with the same mean, but its variance is going to be scaled down by a factor of 1 on n. And so a reasonable question to ask next would be, okay, we know the distribution of our data, we know the distribution of our sample mean, what do we know about the distribution of the variance of these samples? Because even though my samples, my data are drawn from a known distribution, if I were to calculate the sample variance, that is going to change from sample to sample. Okay, and so let's remind ourselves of the formula for sample variance. So it's s squared is equal to the sum from I equals 1 to n. We sum over all the things in our sample of xi, which is a bit of data, minus x bar, which is the sample mean, squared. And then we scale that by n minus 1. Let's suppose that instead of using a sample mean here, we use the population mean, which we actually do know in this case. And so we can rewrite this, instead of using a lowercase s, we're going to use an uppercase s. We're going to represent this as a random variable. So we're going to have 1 on n minus 1, which is just a scaling factor, times the sum from I equals 1 to n of xi, which is, we can replace that by random variables, minus x bar, we're going to replace that with the population mean. So we're just going to get the sum of xi squared. Well, hang on, we know that each xi is distributed as a standard normal distribution, don't we? And we also know that when we take the sum of the squares of a set of independent standard normal distributions, we get a chi-square distribution with n degrees of freedom. And so we can rewrite this equation as n minus 1 times s squared, which is going to be a random variable representing our sample variance, is going to be distributed as a chi-square distribution with n degrees of freedom. Well, this is a good start, but there's two major changes that we're going to make to this when we're doing this problem in reality. And the first one of these is basically this distribution here. We're not going to have data drawn from a standard normal distribution all the time. And so we need to consider the case where this variance is not equal to 1. It's in general equal to some variance sigma squared. And we also need to consider the case where our mean is non-zero. And in particular, where we actually don't know our mean. And so we have to substitute a sample mean, x bar. So let's consider a new set of data, yi, which is normally distributed with some general mean mu and some general variance sigma squared. And we can still write out our formula for the sample variance like this. N minus 1 times s squared is the sum from I equals 1 to n over each of the observations of yi minus y bar squared. And so we want to try and get into the situation we had before, where what we had in this summation was a standard normal distribution, because then we can essentially say this distribution is chi-square. And so to get that, the first thing we need to do is try and get the variance of what's inside these brackets to that of a standard normal distribution. So if we go n minus 1 times s squared, and we divide this by the population variance, whatever it is, well, this is going to be equal to the sum from I equals 1 to n of yi minus y bar divided by sigma squared. Well, now what we have in these brackets looks a lot more like a standard normal distribution, because we're taking a general normal distribution and minusing its mean, it's not a population mean, it's a sample mean, and dividing by its standard deviation. And so it's quite close if we had the population mean in here. We only have the sample mean. And so because we're not using the population mean, because we're using the sample mean, which depends on each piece of data, this is almost going to be the sum of n independent standard normal distributions squared, almost, but not quite. There's one small change we need to make. And so if we replace all these data with, so s squared with capital S squared to be a random variable, and replace all these yi's with capital yi's, and replace this y bar with a capital Y bar, because this is going to be random as well, then what we're going to get is we're going to get each of these, going to get a sum from 1 equals n of each of these standard normals, but the fact that we're using this sample mean rather than the population mean it's going to work out that sort of gets rid of one of our n independent standard normal distributions. And so what we get in the end is a sum from 1 to n minus 1 of a bunch of standard normal distributions. And so now we can say, okay, in general, we had this sort of simple case here where our data was really nice, but in general we can say that n minus 1 times our, the distribution of our sample variance divided by the true population variance, it's going to be chi squared with n minus 1 degrees of freedom. And this should be relatively familiar. Just like when we tried to test for the sample mean, we had a t distribution with n minus 1 degrees of freedom. So too, when we're calculating the sample standard deviation, we lose a degree of freedom because we have to use the same bits of data again to calculate the sample mean. So this is the result that we're particularly interested in. Okay, this is going to be true in general, even if we've got data that has, not a mean of 0 and not a variance of 1. This is always going to be the case, that n minus 1, where n is the sample size, divided by sigma squared, which is the true population variance. When we multiply that factor by the distribution of any sample variance, it's going to be distributed with this very standard distribution, this chi square with n minus 1 degrees of freedom, which, as we know from before, is the sum of the squares of n minus 1 independently distributed standard normal distributions.